James Lovelock, a British scientist, stated, "If you start any large theory such as quantum mechanics, plate tectonics, evolution, it takes about 40 years for main science to come around." Thomas Kuhn, an influential historian of science, stated that scientists mold their interpretations of the natural world to an established line of reasoning called a paradigm that can remain unchanged for a long time until an inspired thinker proposes a radically new idea that works better and forms the basis of a new paradigm. Almost immediately, the broader scientific community scraps old ideas and formulates new ones consistent with the new idea. Kuhn called such abrupt changes in thinking a scientific revolution. In geology, a scientific revolution took place following the proposal of the theory of plate tectonics, often called simply plate tectonics, which states that the outer layer of the Earth, the lithosphere, consists of separate pieces or plates that move with respect to one another. This theory required geoscientists to cast aside interpretations rooted in the older paradigm of fixed continents and led to a complete restructuring of how geologists think about Earth history. These are the key elements of plate tectonics. First, we will focus on lithospheric plates and distinguish the three types of plate boundaries. Next, we will characterize the nature of geologic activity that occurs at each boundary. Thirdly, we will look at hotspots and other special locations on the plates and examine the breakup and collision of continents. And finally, we will consider the different models proposed to explain why plates move and measurements that define rates of movement. In 1912, the meteorologist Alfred Wegener amply described what he called continental drift, expanded in his 1915 book, The Origin of Continents and Oceans. And the scientific debate started that would end up 50 years later in the theory of plate tectonics, starting from the idea that the present continents once formed a single landmass, which was called Pangaea, that drifted apart, thus releasing the continents from the Earth's mantle and likening them to icebergs of low-density granite floating on a sea of denser basalt. But without detailed evidence and a force sufficient to drive the movement, the theory was not generally accepted. The Earth might have a solid crust and mantle and a liquid core, but there seemed to be no way that portions of the crust could move around. In other words, what caused the crust to move? Also, how could a felsic continent, which has less density, plow through the oceanic crust, which is mafic and has a higher density? The idea of plate tectonic theory is very powerful. It provides geologists with a unified mechanism that explains igneous, sedimentary, and metamorphic rocks. It helps explain the distribution of earthquakes and volcanoes, the origin of continents and ocean basins, the distribution of fossil plants and animals, the genesis and destruction of mountain chains, and continental drift. The crust and mantle of the Earth are further subdivided into two layers, the lithosphere and the asthenosphere that we talked about in our last lecture. The lithosphere is the relatively rigid, non-flowable outer 100 to 150 kilometer thick layer of the Earth, constituting the crust and the top part of the upper mantle. The asthenosphere is the layer of the upper mantle that lies below the lithosphere between 100 and 150 kilometers and 350 kilometers deep. The asthenosphere is relatively soft and can flow when acted on by force. Buoyancy states that floating solids displace water equal to their mass. In other words, an iceberg sinks until the mass of water it displaces is equal to the total mass of the iceberg. If 80% of the iceberg is below the top of water, then ice has a density of 0.8 grams per cubic centimeter. The concept applies to the lithospheric plates riding on the asthenosphere. The continental plate will ride higher than the oceanic plate because the continental plate is less dense than the oceanic plate, and both are less dense than the water. Remember that the lithosphere includes the crust and the top portion of the upper mantle down to 100 to 150 kilometers. The oak is equivalent to the thickness of the top portion of the upper mantle. The cork is equivalent to the continental crust, and the pine is equivalent to the oceanic crust. The oak and the cork, the continental lithosphere, or the oak and the pine, the oceanic lithosphere, are equivalent to the lithosphere being buoyed by the water or the asthenosphere. There are two general types of plates, marine and a combination of marine and continental plates. There are three types of plate boundaries: convergent, which are collision zones where two plates come together; divergent, a ridge where two plates separate in opposite directions; and transform boundaries, where plates slide past one another either in opposite direction or in the same relative direction, but at different velocities. Plates move at a rate from 1 to 15 centimeters per year. Your fingernails grow at a rate of 2 centimeters per year. 2.54 centimeters equal 1 inch. Tectonic plates display a variety of sizes and shapes. Plus, they have changed the size and shape throughout their history, or the history of the Earth. This is a world seismic map that shows the location of earthquakes and their concentrations. The heaviest zones are at convergent boundaries, where two plates collide. The lighter red zones are earthquakes along the divergent boundaries and transform boundaries. The area around the Pacific Ocean is known as the Ring of Fire because of the high number of volcanoes that are associated with convergent boundaries. It is very important to know the difference between a passive and an active margin. Associated with continental plates are both passive margins and active margins. Passive margins occur on the border of the continental plate that is adjacent to spreading centers. They have a very wide continental shelf and have no volcanism or earthquakes. An example of this is along the eastern seaboard of North America. To the east of the seaboard, in the middle of the Atlantic Ocean, is the Mid-Atlantic Ridge divergent zone. The North American plate begins there and is slowly pushed eastward. On the other side of the plate, along the western seaboard, is an active zone. It is active because it is an area of subduction or a subduction zone. Because the continental mass of North America is less dense than the Juan de Fuca marine plate, the Juan de Fuca marine plate subducts beneath the North American plate, creating a zone of very active earthquakes and volcanism. It is also characterized by a short continental shelf. We can distinguish among three types of plate boundaries simply by the relative motion of the plates on either side of the boundary. There are three plate boundaries: divergent, convergent, and transform boundaries. At a divergent boundary, two plates move away from the axis of a mid-ocean ridge, and new oceanic lithosphere forms. As the lithosphere thickens away from the ridge axis. They are also called spreading boundaries, mid-ocean ridge, and ridge. At a convergent boundary, two plates move towards each other. The downgoing plate sinks beneath the overriding plate in a process known as subduction. Convergent boundaries are also called convergent margins, subduction zones, and trench, because a deep trench is always associated with subduction zones. At a transform boundary, two plates slide past each other on a vertical fault surface. Plate material is neither created nor destroyed. It is also called a transform fault or a transform. Each type of boundary that we've just mentioned of the three boundaries looks and behaves differently from the others, as we will see in the next few slides. At a divergent boundary or spreading boundary, two oceanic plates move apart or diverge by the process of seafloor spreading. Magma wells up to fill the gap as the plates are moving apart. As the magma cools, it adds to the material to each plate, and the ocean basin expands in width over time. In the last chapter, we discussed upwelling convection flow within the mantle. When the convection flow beneath marine plates and occasionally underneath continents reaches about 110 kilometers beneath the surface, the temperature and pressure regime is perfect for the solid peridotite to melt. The melting magma burns through the lithosphere along a line. The higher mantle temperature causes the crust to bow and thin, causing breakage and faults along this thin, long line. The magma wells up through the fractures, forming new crust, while the asthenospheric convection pulls the plates apart, creating a mid-ocean ridge. An example is the Red Sea between Africa and Saudi Arabia, which is a long, thin basin with very young crust. This is time one formation of a new ocean basin. During the mid-stage of seafloor spreading progression, the ocean begins to widen even more. New seafloor is added at the mid-ocean ridge, and continents move further apart. An example is Greenland, the separation of Greenland and the European plate by the mid-Atlantic ridge. The late stage of seafloor spreading progression is indicated by a mature wide ocean basin. We see a linear increase in age with distance from the central ridge. In other words, the edge of the ocean basin has the oldest material, and at the ridge we find the youngest materials. An example is the Atlantic Ocean, in which North America and Europe are separated by the mature Atlantic Ocean basin, and in the southern hemisphere, South America and Africa are separated by a mature southern Atlantic Ocean. Mid-ocean ridges are linear mountains that are in the Earth's ocean basins. Although ocean ridges are found all over the world, a perfect example is the Mid-Atlantic Ridge that snakes north and south through the entire Atlantic Ocean. It is an elevated ridge above the abyssal plain, or the deepest part of the ocean. The ridge rises 2 kilometers above the abyssal plain and is about 1,500 kilometers wide. Running along its center is an axial rift valley that is 500 meters deep and 1 kilometer wide on average. It is very symmetric with matching normal faults stair-stepping upwards away from the rift. Numerous eruptions occur along the rift and within the rift valley. According to current models, the asthenosphere flows very slowly upward beneath the lithosphere, about 2 centimeters per year on average. At about 30 to 60 kilometers beneath the seafloor, up to 15% of the peridotite melts. The resulting magma formed contains more silica than the ultramafic rock from which it formed. Some of the rising magma mush accumulates in magma chambers at a depth of 2 to 7 kilometers beneath the sea floor. Some material solidifies along the sides of the magma chamber to form the phaneritic coarse-grained mafic rock gabbro. Some rise even higher into vertical normal fault fractures, cools quickly to form basalt dikes, and the magma that makes it to the surface of the seafloor spills out of small submarine volcanoes as lava. The lava that spills out of the small volcanoes cools rapidly to form piles of meter-wide basalt blobs called pillow lava or pillow basalts. This is an image of recently erupted pillow basalts from the Juan de Fuca Ridge. So the newly formed oceanic crust has three distinct layers. A layer of pillow lava overlies a layer of basalt dikes, which in turn overlies a layer of gabbro. Within mid-ocean ridges, black smokers are found along fracture zones within the ridge valley. Seawater enters the fractured crust in one locality, flows downward, gets heated as it nears magma. The hot water dissolves minerals and cycles back out of the newly formed crust to another locality. When the water reaches the ocean, it rapidly cools and minerals, mainly sulfur, precipitate out to form the black smokers. Benthic biological communities that never see the sun depend on nutrients found in the dusty chemical deposits and hydrothermal fluids that are emitted from black smokers. Several geologic phenomena occur as the crust moves away from the mid-ocean ridge. First, new crust is closer to the ridge, and older crust is further away. The oldest crust is found on the edges of the ocean basins. The average maximum age of the ocean floors is about 180 million years old. Secondly, the lithosphere thickens as it moves from the mid-ocean ridges. As the lithosphere cools, it becomes thicker, absorbing a portion of the asthenosphere. Remember that the defining temperature between the lithosphere and the asthenosphere is 1,280 degrees centigrade. Sediments are thinnest at mid-ocean ridges and thicken towards the edge of the basin adjacent to the continents. Several geologic phenomena occur as the crust moves away from the mid-ocean ridges. First, new crust is found closer to the ridge, and older crust is further away. So, the oldest crust is found on the edges of the ocean basins. The average maximum age of the ocean floor is 180 million years old. Secondly, the lithosphere thickens as it moves from the mid-ocean ridges. As the lithosphere cools, it becomes thicker, absorbing a portion of the asthenosphere. Remember that the defining temperature between the lithosphere and the asthenosphere is 1,280 degrees centigrade. Sediments are thinnest at mid-ocean ridges and thicken towards the edge of the basins adjacent to continents. Lithospheric plates move towards one another at convergent boundaries. One plate is always oceanic, and the plate that subducts is also always oceanic. Subduction recycles the oceanic lithosphere and is always balanced by seafloor spreading. Once a marine lithospheric plate reaches an age of 10 million years, its density is greater than the asthenosphere. The overriding plate is always less dense than the subducting plate. The overriding plate may be a younger plate or a continental plate. Continents are less dense than any marine plate. Remember that continents are felsic and have an average density of 2.7 grams per cubic centimeter, and the mafic marine crust has an average density of 3.0 grams per cubic centimeter. Therefore, continental plates can never subduct. The subducting plate descends at an average of 45 degrees. We know this due to the location of thousands of seismic foci at subduction zones. The zones of earthquakes are called the Wadati-Benioff earthquake zones, a planar zone of seismicity corresponding with the downgoing slab in a subduction zone. Different motions or differential motions along the zone produces numerous earthquakes, the foci of which may be as deep as about 660 kilometers or 420 miles. It has been suggested that the plates are consumed or assimilated in the lower mantle. There are a number of unique geologic features associated with both marine and marine continental subduction. A subduction trench that defines the trace of a convergent plate boundary. An example would be the Mariana Trench located down the southwestern Pacific Ocean. An accretionary prism or ridge is a wedge-shaped mass of sediments and rocks scraped off the top of the downgoing plate and accreted onto the overriding plate. Volcanic or continental arc is a curving chain of active volcanoes found on the overriding plate formed adjacent and parallel to the convergent boundaries. A volcanic arc would be like the Japanese islands, and the continental arc would be like the Cascade Mountains. Four arc basins is a basin or flat-lying sediments located between the accretionary prism and the volcanic arc or continent. And finally, the back arc basin is found on the overriding marine plate behind the volcanic arc. Accretionary prism is a deformed sediment wedge. Sediments are scraped off of subducting plates, much like a rug being shoved up against a wall or a bulldozer pushing soil in front of it. This thrusts them onto the overriding plate. Contorted prism sediments can be pushed above sea level. For example, two examples that listed here are the Olympic Peninsula and the island of Taiwan. The chain of volcanoes known as a volcanic arc develops behind the accretionary prism. The magma that feeds these volcanoes form above the surface of the downgoing plate, where the plate reaches a depth of about 150 kilometers or 93 miles below the Earth's surface. If the volcanic arc forms where an oceanic plate subducts beneath continental lithosphere, the resulting chain of volcano grows on the continent and forms a continental volcanic arc. In some cases, compression between the converging plates produces a belt of faults in the region behind the arc. If the volcanic arc forms where one oceanic plate subducts beneath another oceanic plate, the resulting volcanoes form a chain of islands known as a volcanic island arc. Back arc basins. A marginal sea or back arc basin is a small ocean basin behind an island arc. It forms either in cases where subduction happens to begin offshore, trapping oceanic lithosphere behind the arc, or where stretching of the lithosphere behind the arc leads to the formation of small spreading ridge behind the arc. Transform boundaries occur where two lithospheric plates slide past one another. Lithospheric plates are not created or destroyed in these zones. Many transforms offset spreading ridge segments. For example, when you look down the mid-Atlantic ridge, you see perpendicular lineations spreading away, those from the perpendicular to the mid-ocean ridges. These are transform boundaries. However, some transforms cut through continental crust, like the San Andreas fault, where we have two plates rubbing against one another. the North American plate going to the southeast and the Pacific plate going to the northwest. These zones are characterized by a large number of or volume of earthquakes and also are noted for their absence of volcanism. Originally, researchers assumed that the entire length of a fracture zone was an actively slipping fault that displaced mid-ocean ridge segments. They discovered instead that earthquakes happen only along the segment of the fracture zone that links the end of a ridge segment to the end of the next ridge segment. Earthquakes don't occur along the portion of the fracture zone that extends beyond the ends of the ridge segments out into the abyssal plains. So these portions of fracture zones are not actively slipping faults. Slip occurs only along the segment of fracture zones between the two ridge segments. Plates on opposite sides of inactive fracture zones move together as one plate. Wilson introduced the term transform boundary for the actively slipping segment of a fracture zone between two ridge segments, period. Not all transform boundaries link ridge segments, and not all transform faults occur in oceanic lithosphere. A few cut across continental lithosphere. The San Andreas Fault, for example, which cuts across western California, defines part of the boundary between the North American plate and the Pacific plate. The portion of California that lies to the west of the fault, including Los Angeles, is part of the Pacific plate, while the portion that lies to the east of the fault is part of the North American plate. Geologists refer to a point where three plate boundaries intersect as a triple junction. We name triple junctions after the type of boundaries that intersect at them. For example, the triple junction formed where the southwest Indian Ocean ridge intersects two arms of the mid-Indian Ocean ridge is a ridge-ridge-ridge triple junction, the figure on the left. And the triple junction north of San Francisco is a trench transform triple junction, the figure on the right. Not all volcanoes on the Earth are plate boundary volcanoes. The currently erupting volcanoes of the Big Island of Hawaii lie over 4,000 kilometers from the nearest ridge or trench. And Yellowstone National Park, which occupies the remnants of a huge volcano that erupted during the past 1 million years, lies well into the interior of the North American plate. Worldwide, geoscientists have identified about 100 volcanoes that exist as isolated points, not as a consequence of movement at a plate boundary, and refer to these points as hotspots. Many hotspots lie in the interior of plates away from plate boundaries, but some lie on mid-ocean ridges. Hotspot volcanoes form above a localized magma source whose position in the mantle stays fixed, more or less relative to the moving plate above. The active volcano represents the present-day location of the magma source, whereas the associated chains of inactive volcanic islands represent locations on the plate that were once over the magma source, but progressively moved off the source as the plate moved. Once the moving plate has carried the volcano away from the magma source, the volcano becomes inactive. But as long as the source persists, melt continues to be produced, so a new, younger volcano grows. Eventually, the younger volcano moves off the hotspot and becomes inactive, and another, still younger one forms. The chain of inactive volcanoes that formed in succession is now known as a hotspot tract. Hotspot volcanoes form above a localized magma source whose position in the mantle stays fixed, more or less relative to the moving plate above. The active volcano represents the present-day location of the magma source, whereas the associated chain of inactive volcanic islands represent locations on the plate that were once over the magma source, but progressively moved off the source as the plate moved. Once the moving plate has carried the volcano away from the magma source, the volcano becomes inactive. But as long as the source persists, melt continues to be produced, so a new, younger volcano grows. Eventually, the younger volcano moves off the hot spot and becomes inactive, and another still younger one forms. The chain of inactive volcanoes that form in succession is now known as the hot spot tract. As the islands move off of the hot spot, they begin to sink and form what is known as a guyot, G-U-Y-O-T. And I'll give you the definition of a guyot here as soon as I find it. A guyot is a seamount that had a coral reef growing on top of it so that it is now flat on the surface or flat crested. What is the source of the magma for a hot spot? Most researchers favor a model in which magma forms at the top of the mantle plume, a column of very hot rock rising from deep in the mantle up through the asthenosphere to the base of the lithosphere. Rock in the plume, though solid, is soft enough to flow and rises buoyantly because it is less dense than the somewhat cooler rock of the surrounding mantle. According to the plume model, when the hot rock of the plume reaches the base of the lithosphere, it starts to melt and produces magma that seeps up through the lithosphere. Some of this magma reaches the Earth's surface and erupts to produce a hot spot volcano. A continental rift is a linear belt along which continental lithosphere undergoes a horizontal stretching in a direction perpendicular to the trend of the rift and thinning in the vertical direction. Geologists refer to the overall process of stretching and thinning as rifting. In the upper 15 kilometers or so of the continental crust, which is relatively cold and brittle, stretching causes rock to break and faults develop. These faults are known as normal faults. During this faulting, blocks of the upper crust slip down along the fault surface, leading to the formation of low areas called a rift valley that gradually becomes buried by sediment. At greater depth, continental rock is warmer, so stretching can take place plastically without breaking the rock. As the continental lithosphere thins during rifting, the underlying hot asthenosphere rises, and the asthenosphere starts to melt, just as it does beneath mid-ocean ridges, producing magma that rises up into the crust. Some of the molten rock reaches the surface and erupts at volcanoes along the rift. If rifting continues for long enough time, the continent will break in two, and a new ocean ridge will form, and seafloor spreading will begin. We refer to places where rifting takes place today as active rifts. Active rifting produced the Basin and Range Province, a region in the western United States in which numerous narrow mountain ridges are separated by flat valleys. The ridges are called horst and the valleys are called grabens. The mountain ridges are blocks of crust, or the horsts are blocks of crust that slip down faults, whereas the valleys, or the grabens, are sediment-filled basins. The Basin and Range Province is the widest rift on our planet. Another active rift, the East African Rift, extends in a north-south direction for over 3,500 kilometers. On the ground, it consists of a deep rift valley bordered on both sides by high cliffs formed by faulting or normal faults. Along the length of the rift, several major volcanoes smoke and fume. These include snow-crested Mount Kilimanjaro, towering about 6 kilometers above the savanna. The East African Rift links to the Red Sea and the Gulf of Aden, both of which are narrow oceans in which rifting has gone to completion and new mid-ocean ridges have formed. At its north end, the Red Sea Rift dies out in the Gulf of Suez. Geoscientists refer to the process during which two buoyant pieces of the lithosphere converge and squeeze together as collision. Not all collisions involve two full-size continents. Some involve island arcs or continental slivers, hotspot volcanoes, or broad areas of unusually thick ocean crust called oceanic plateaus. Regardless of what collides, when a collision finishes, the convergent plate that once existed between the two colliding pieces ceases to exist. Collisions have yielded some of the Earth's highest mountain ranges, such as the Himalayas and the Alps. They have also produced major mountain ranges in the geologic past. These old ranges eventually eroded away, so today we see only their relics. For example, the Appalachian Mountains in the eastern United States formed as a consequence of three collisions. After the last one, the collision between Africa and North America that happened about 280 million years ago, North America became a part of the Pangea supercontinent. We'll discuss collisional mountain belts further in Geology 202. When geoscientists first proposed plate tectonics, they speculated that the plates move simply because convection flow in the asthenosphere actively dragged them along, as if the plates were rafts on a flowing river. In fact, early images depicting plate motion showed simple elliptical convection cells, flow paths in the asthenosphere. In these images, the cells were positioned such that the asthenosphere flowed up beneath mid-ocean ridges and sank down at subduction zones. Gradually, geoscientists came to the conclusion that while convection flow does occur within the asthenosphere, it does not drive plate motion alone. The local direction of convection flow do not necessarily control the local direction of plate motion. Researchers now prefer a model in which convection plays a role in plate motion, but is not the whole story. Two other forces, ridge push and slab pull, contribute significantly to driving the plates. Conceivably, convective asthenosphere flow may either speed up or slow down plates depending on the orientation of the flow direction relative to the movement direction of the overlying plate. New research also suggests that the asthenospheric flow pushes on downgoing plates and affects the angle at which they sink. Ridge push force is an outward directed force that contributes to moving plates away from a mid-ocean ridge axis. It develops because the lithosphere of mid-ocean ridges lies at a higher elevation than that of the abyssal plains. Gravity causes the elevated lithosphere at the ridge axis to push on the lithosphere that lies further from the axis, making it move away. As the lithosphere moves away from the ridge axis, new hot asthenosphere continuously rises, providing material from which new crust and new lithospheric mantle form. Slab pull force arises simply because lithosphere that was formed more than 10 million years ago has become denser than the asthenosphere, so it can sink into the asthenosphere. Therefore, once any part of an oceanic plate starts to sink, it gradually pulls the rest of the plate along behind it, like an anchor pulling down the anchor line. How fast do plates move? It depends on your frame of reference. The movement of one plate with respect to another is called relative plate velocity, whereas the movement of a plate with respect to a fixed location inside the Earth is called absolute plate velocity. Imagine two cars, A and B, speeding in the same direction down the highway. From the viewpoint of a tree along the side of the road, A zips by at 100 kilometers an hour, while B moves at 80 kilometers an hour. But relative to B, A moves only 20 kilometers an hour. The motion of a car relative to the tree represents its absolute motion, whereas the motion of one car with respect to another represents its relative motion. In this image, we see relative and absolute plate velocities. The black arrows show the rate and direction at which the plate on one side of the boundary is moving with respect to the plate on the other side. Outward pointing arrows indicate divergent boundaries, inward pointing arrows indicate subduction or convergent boundaries, and parallel arrows show transform motion. The length of an arrow represents the velocity. The red arrow shows the velocity of the plates with respect to a fixed point in the mantle. Working with the calculations given in the book, motions on the Earth today occur at rates ranging from 1 to 15 centimeters per year. By using the Global Positioning System, GPS, the same technology that automobile drivers can use to find their destinations, we find that we can detect displacements as small as 2 millimeters per year. Since plates move 5 to 75 times this rate, we can indeed see the plates moved, and this observation serves as the ultimate proof of plate tectonics. The rates of plate motion are very slow in comparison to the rate at which we walk or drive. In fact, plates move at about the rate that your fingernails grow. But even at those slow rates, plate motion can yield large displacements given the immensity of geologic time. For example, at a rate of 2.5 centimeters per year, or about an inch a year, a plate can move 25 kilometers in a million years and 2,500 kilometers in 100 million years. At this rate, the Atlantic Ocean opened to its present width 4,500 kilometers in 180 million years since the breakup of Pangaea. Taking into account many data sources that define the motion of plates, geologists have greatly refined the image of continental drift that Wegener tried so hard to prove nearly a century ago. We can now see that the map of our planet's surface has evolved radically during the past 400 million years, and even before. Here we see the assembly and later breakup of Pangaea during the past 400 million years ago. 400 million years ago, we had a continent called Pangaea. Pangaea broke up, formed Pangaea. Pangaea, since 250 million years ago, Pangaea has separated into the continents that we know today. I want to thank you so much for taking this geology class. I've really enjoyed teaching you. This has been a new learning experience for me with this asynchronous class and putting together all these videos for you. And I hope that you have enjoyed the class and able to take something away from this class that you can use in the future.